All right. Everybody good? So this is computable, right? Sometimes we use M. Why do we use M? Turing machine, right? All right. So now you can ask, what is uncomputable, right? What is to say the problem's not computable in polytime, right? That's pretty hard. And you don't have intuition for it. And I've given it to plenty of students, and they always get them wrong, right? So how do we do it? How do we write down a statement that says it's uncomputable? What did you?
Just the negation.
You just negate it. You just negate it, right? Right? You learned in our first week of for alls how to negate things, right? People struggle with this. The intuition gets them wrong, right? It's helpful sometimes, you know. Is George right? Yeah, sometimes you have to just mechanically do it yourself, right? Just mechanically do it, right? Simply take the negation. What's the negation? The exists turn into a for all. The for all turns into an exists. The equal turns into a not equal, right? We just take the negation, right? And now we have to understand this, right? P is uncomputable. Why is it uncomputable? It's uncomputable because every Turing machine fails to compute it, right? M fails to compute it. Why does it fail to compute it? It might get the answer right on every input but one, right? It fails to compute it if there's one input on which it fails to compute it, right? Why does N fail to compute P on I? Because it's got the wrong answer on this input, right? All right. So how do we prove this? I want to prove the halting problem is uncomputable. I let the adversary give me an arbitrary Turing machine algorithm, right? Then I study this algorithm, and I had to come up with an input. That's pretty hard, right? It's hard to prove these things, right? And then I win if the algorithm that the adversary gave me on the input I produced fails to give the right answer. Right? Everybody buy that? And the only time I've seen a proof of this is for the halting problem. And why is that? Well, again, you just write down the first order logic statements of everything. You play the game, and it falls out without thinking, right? It really is that easy. If you don't understand the game, then it looks like hocus pocus. We're just like, what are they doing, right? But if you do it right, we're supposed to cover this in 2001, that the halting problem is undecidable. And all we do is play the game, all right? All right, so here's one that you should know already the answer to, because I've given it to you already. I've given this problem to people many times, right? Are people up for, is this true or false? It's true. It's true for the halting problem, right? Let's just play the game, all right? The order matters. Here, look at, when you see this, you should feel pain in your body, right? Right? Just trust the game, right? So it says for all inputs, the adversary gives me an arbitrary input, right? Now, I have this input. either it halts or it doesn't halt. Do I know which it does? No, because I don't know how to solve the halting problem, right? I don't know whether, right? In fact, have you ever heard the word constructive proof versus non-constructive proof? What we've been doing throughout this whole course is constructive proofs. The way I prove that there exists something is I construct it, right? We're going to prove here a non-constructive proof. We're going to prove that something exists even though I don't know how to construct it. Right? Does that make sense? All right. So I don't know whether the answer to the halting problem on the adversary's input is yes or no. I don't know, but I know it's either yes or no, right? So I'm going to come up with two algorithms. My first algorithm, what does it do? On every input, it says yes. And what does my second algorithm do? On every input, it says no, right? Now, I don't know which of these gives the right answer, but one of them does, right? I know that there exists an algorithm that solves the halting problem on this problem, right? On this input, because one of these gives the right answer, right? Does that make sense? Non-constructive proof, right? All right, so Gödel proves some really cool things, right? He proves that there's no proof system that will prove everything that's true under the reals, right? He proves two things. He proves the completeness theorem that says if something is true in every model, if it's a tautology, then there's a proof for it, right? That's an amazing statement, right? The completeness theorem says everything that's true in every model has a proof. But he also proves that if you restrict yourself to the reals, then it might not have a proof. And in order to prove that, you have to express what does your Turing machine do, right? I want to say, can I say in, right? I'm claiming you can say anything in math and it with for alls and exists. And you say, really? It seems like such a weak language, right? But here's something I want to say in math. I have a concrete Turing machine. I have a concrete input, and I want to say M halts on I, right? How do I say it? Well, let's say in English first, right? I want to say there exists a computation in which when you run M on I, that's the computation that runs, and it's a halting computation, right? Now, how do I say that when I'm working? Oh, sorry, I said we're working over the reals. I lied to you. He only works over the positive integers, all right? So over the positive integers, I only can say there exists an integer, right? So what does Gödel do? He's brilliant. He encodes. This is before computer science. This is before they were encoding things in bits, right? Shannon later in the 40s talked about how everything's been encoded in bits. But Gödel did this before. He encodes it with prime numbers, products of prime numbers. He says, I'm going to take an integer to encode the computation, right? So there exists an integer that encodes the valid computation. And then what do I want to say? I want to say for every time step, this integer, which is encoding this computation, is taking a valid step for my Turing machine, right? And, right, that's pretty amazing, right? We can do this. And model of computation. You know, Turing machines is a model of computation. Java is a model of computation. And this is just another model. All right, let's see if we can get rid of this thing, because you know I hate it. All right. How does a table compute? All right, so what is an algorithm? One requirement of an algorithm is that it has a finite description, right? You don't want infinitely long algorithms. And this algorithm is the finite table. So it has two columns. The first column lists possible inputs, and the second column lists what the output is. So if you want to do a little matching, you can see that what this is doing is multiplying, all right? And so how does it compute? Well, you give me some input, and like what does a computation do? You give it an input, and it does its best to give an output. And in this case, if the input is in the left column, then it outputs what's in the right column, right? And if it's not there, then it panics, right? Yeah? Yeah, yeah. So how does... Oh, the input is a pair of numbers. Yeah, sorry. The input here is a tuple of numbers, and what we're doing is we're multiplying them. All right, so the bottom one, the input's 2 and 4, and the output's 2 times 4, right? Everybody understand this model? And so the question is, what can this compute? What can we say about it, right? Can this model of computation, the table, can it multiply 2 arbitrary integers? Not this table. Is there a table that can multiply 2 inputs? No, that's what I said. Every description needs to be finite. All right. Right. So can it multiply these? Yeah. Can it multiply these? No. Right. So we want to be able to write down. This is, of course, in logic, right? What I want you to be able to do is write down things in, I'm going to call it first order logic, and know what they mean. So everybody should be able to read this now and hope they know what it means. It means for any k, you give me an arbitrary k, right? The adversary gives me an arbitrary k. And then I can produce a table. And what does that table do? Well, it's an algorithm within my model. And what is it able to compute? You can give me any values of x and y that are at most k. And then this table will multiply x and y together, right? People following what this says? Do people believe it's true? Is it true? Right? All right. Right? Sure, it's true. What is it saying? Adversary gives me a k, right? Then this guy's going to give you a table like this. How many entries is it going to have? Well, for every value of x, there are k values of x, there are k values of y. The size of this table is k squared, right? Gives you, and then the adversary gives you 2 values, x and y, and sure enough, the table can multiply them, right? Everybody buy this? All right, so here's a different table. There exists a table that for every x and y knows how to multiply them. Is that true? How many people think that's true? How many people think it's not true? What? No, I keep saying this, guys. table's finite. No, table's always finite. Right? It's saying there exists a table, it's finite. Says that for any x and y, it knows how to multiply. All right? So it's not true, right? And how do we prove it's not true? We kind of play the reverse game, right? He's claiming, I mean, they're playing the game here, but the prover's going to lose, right? He says, oh yeah, there exists a table, so I give you an arbitrary table. And the adversary says, yeah, your table better be finite, right? It can't list all, there are an infinite number of inputs, right? There are an infinite number of x and y's. So the adversary finds some, the adversary knows your table, right? And is coming up with a pair x and y that aren't listed in the table, right?